Taking attendance. Taking attendance on the third day is a little risky, so I know we've crammed your heads with a lot more information than maybe you typically used to in the summer. So today we're going to cover light stuff like principal component analysis, things like that. No big deal. But honestly, we're going to make it light. We'll cover principal component analysis, but in a very conceptual way. So really to just try to drive what we're really after here, which is try to understand this idea of unsupervised learning. So I'm going to pretend I did it on purpose, but I didn't wear my name tag today because a lot of time data doesn't come with labels, right? Most of the time data doesn't come with labels. So we have this idea of supervised learning, which is what we've been talking about so far. The vast majority of machine learning happening in the world today is the supervised form. It's where you have data that comes with inputs and outputs. And what you want to do is get a mapping from the inputs to the outputs, right? So you've got pictures of dogs, and you've got a folder that says these are dogs, or you got certain flowers, and you know the labels of those flowers. You give the network examples of the inputs of a specific category, and you say learn this category. Okay, so that's supervised learning, where we have the ground truth, some sort of ground truth that we want the model to learn from new examples, from previously trained examples of inputs and outputs to some new examples. So going to learn the mapping between input features and output labels. But there's a whole other class of machine learning called unsupervised learning, which we haven't discussed in any real detail yet, where you're not actually providing a model with any ground truth, which makes me wonder, well, what do you want it to learn? So the goal essentially is to discover underlying structure of the data. There might be some underlying structure that, for example, there might be categories that are there, but you don't know the labels, right? So, look around the room today, we could cluster up into different groups, maybe by age, or by gender, or by shirt color, right? You sort of have pretty uneven distributions there. And so these are structure that exists within the data, but you don't necessarily provide that information. In the case of unsupervised, you're not providing those categories. So I just want to make the point that most learning is unsupervised. So how do we build the brain? So children, babies, almost all animals don't get labeled data. Right? Every once in a while you might point to something and say this is a whisker or something like that. But for most of our life, most of our experience, we are just engaging with the world, and our brain is changing. Our brain is learning stuff. What's it learning? We know it's learning stuff because we see that cortical structure is learned during the course of early development. In fact, it's learned throughout our entire lifetime, but specifically, particularly during early development, we see that there's these critical windows where certain kinds of structure that we know is there has to get there based on experience. So there's a series of famous studies that were done on cats that were reared in kittens, actually, in very impoverished environments. Not quite this impoverished. This is sort of a mock-up of it. It wasn't quite this small. But the idea was you put a cat in an environment that only has vertical lines. So they never encounter horizontal. They don't encounter horizontally oriented edges. And what you'll find is if you measure the cortical responses in these cats, they will have essentially no response to perfectly horizontally oriented edges. So that V1 structure that we talked about, these oriented edges, those basic building blocks of the rest of the features that we encode that brains encode, depend on appropriate developmental experience, which means that the structure is learned, but it's learned in an unsupervised way. Of course, nobody, when you're a baby or when you're growing up, you don't get labels that come along with all of this natural structure that's in the world. Instead, your brain seems to somehow learn it independent of any of that kind of supervised input. And so we're going to talk a little bit about unsupervised learning today, and some of the basic underlying mathematical principles without really going heavily into the math, and then a bit about why we think the brain is doing this kind of unsupervised learning. And then William's going to go a little bit more into some of the specific techniques in the way that this kind of unsupervised learning can actually be instantiated in models. So, supervised learning, we're all familiar. Hopefully, this is all old hat by now. We can do classification. We can do things like regression, where you get examples You feed them to the model, and you give it a new example, and you say, okay, what's this? Is it part of this class or this class? Or regression. I've given you a lot of x's and their corresponding y values, and then I give you a new x, and I say, what's the corresponding y value? So you've got all those examples. Unsupervised learning is something like this. Here's a bunch of points in space. Now let's pretend the color is what is the classification, but that's not fed to the model. The model is asked to basically decide. Let's say we give a model and ask it, tell it that there are 3 different distributions here. Can you please cluster up our data so that there are 3 groups? What are the reasonable groups? So you can see in this case, this is a model that's taken in a bunch of data, a bunch of just x, y coordinates, and it's decided based on some algorithm that these guys belong together and these guys belong together. And it obviously appears pretty reasonable, right? This somehow makes sense that this is a cluster. You can kind of do it intuitively. So there are various means by which this kind of clustering can be done. Not something we're going to focus on. If you're really interested in k-means clustering, that's sort of one of the very fundamental approaches. You basically tell an algorithm, find me this many clusters, and then it tries to make the best guess as to where. So what it really is doing is trying to find like a point that might be the center of a distribution, and then find one that minimizes distance from the center. So it's picked these 3 points, these 3 x's, 3 crosses, and it's said that seems like a good place to put the center of a distribution, and then these are part of that distribution. Anyway, I won't go into detail on that because that's not really a focus of the kind of unsupervised learning we're going to be talking about. Source separation is another form of unsupervised learning. I apologize for the JPEG-ness of this image. Let's say I'm talking and somebody else is talking right next to me, right? Cocktail party phenomenon is a problem, which is something we encounter all the time in a noisy environment. You have to pull out somebody's voice and have a conversation with them and ignore the other person. And we do this intuitively, but how on earth do you do this? How do you separate? Well, the answer is, again, it's sort of a clustering problem. There are certain kinds of features in some dimensional space, right? It has to do with pitch, it has to do with loudness, it has to do with direction. There's various different dimensions that you can use to pull out one source and exclude the other. So this is an important problem in things like sound engineering, or if you want to be able to extract one signal from a different signal when they're intermingled. And a very important, and this is the one area of unsupervised learning we're going to talk about the most, is dimensionality reduction. So we have high dimensional data. This is what we've been kind of a theme throughout the past couple of days. Very high dimensional data. What's a good example of a very high dimensional data structure? An image, right? So every time we open up our eyes, 100 million photoreceptors. That's very high dimensional data. We might want to reduce that dimensionality in order to do things like learning. So we might want to learn on a certain data set, and if there are too many dimensions, the curse of dimensionality, and it becomes very difficult to know where the information is that's predictive of some class. So here's our PCA non-technical introduction to principal component analysis, a very important approach to dimensionality reduction. It's used in many different, across many different industries and different data types. We're not going to be doing PCA when we get to our models, but it is I think it's a very nice introduction to the concept of dimensionality reduction, and sort of gets the basic idea across. In our lab, we do two different types of dimensionality reduction that really kind of depend on something closer to neural networks, and these approaches actually can do things that PCA cannot do. So I think we've actually, not just us in the lab, but as a community, there are techniques that are in some ways more powerful than principal component analysis, but it still is a go-to approach if you're doing working with certain kinds of data. So what is principal component analysis? So I'm going to start off with an example of where it should be obvious how we can throw away a dimension. So let's say our data consists of this distribution. And I should have put a line. Let's say we have a classification test. And we'll put the border here. Right? So all of these are one class, and all of these are another class. And now we want to learn those classes. Well, we've got each data point has two dimensions, x and y. right? And so if we wanted to learn, we might want to feed the model that we're learning both x and y. Or would we? Well, maybe, maybe not. Anybody think why we might perhaps not want to feed it both x and y?
Why does it vary?
Why does it vary? Why is it constant? It has absolutely zero information about class. So if you're trying to figure out the class you're in, and I said divided lines here, telling me the value of y literally tells me nothing. It has no information. It's a constant across all the examples, which means, in a sense, what we could do is chuck it. If we wanted to actually train a model on this data to do classification, we may as well just throw out y. Right? So this is the type of example that makes it very simple and obvious. In really high dimensional data, of course, it's not going to be quite that simple. In real natural data, it's never going to be quite that simple. So what about something like this? So now we have x and y, and let's say, in a classifier that looked like that. So everything here is one class, everything up here. Actually, it is color-coded. Actually, I don't have to draw those lines, right? Here's our categories. Here's red, green, and blue. So those are our categories. And in this case, you might say, well, you really need x and y. It's just telling me x isn't going to quite do it, because there's some examples here that depend on both x and y for their categories. So how can we reduce the dimensionality here? And so that's what principal component analysis allows us to do. So let's say we have highly correlated data here. So what that means is x is very predictive of y. So it's not true, they're not quite independent. The value in the x-axis is not quite independent of the value in y. Can we leverage the fact that these are correlated in order to be able to perhaps reduce the dimensions? And so this is what principal component analysis does. With some fancy math, you can pull out these principal components, which in this case are these vectors. So it's sort of a directional vector that tells us what direction the greatest variation is in. So in other words, the spread of these, think about how are they most spread out? Well, they're most spread out in this direction. That's the first component. And then it's always the case that the second component is orthogonal to that. And so the second direction is the most spread out is this one. Now we found what might actually serve as a new axis. We can rotate the entire distribution. So imagine that this is now the axis, right? So in other words, now we're going to turn this into the x-axis. And then the data looks like this. So what we really did was rotate it around that x-axis. So now that forms the primary axis of the data in this direction. And then we do one last thing. We throw away the y-axis. And we do what this is called projection, right? We project the data. So in other words, if we throw away the y-axis, we just measure where do each of these fall along this new x-axis, and we get this. And what does this look like? Oh, well, it should look familiar. So this looks just like this. It's in fact the same exact thing. So what we've done is we've thrown away a little bit of information. What have we thrown out? Well, we've thrown out information about this other axis that has less spread, but we've preserved the information that carries the most spread. And what you find is, what you can do now, this is in the case of 2 dimensions, you really might not want to do that, right? It might be the case that that y-axis is really going to be quite important. But imagine very high dimensional data. What you could do is you can try to extract a certain number of those components, maybe the first 10, the first 15, and you can even measure how much information might be lost by throwing away the other dimensions. And then you could say, this is good enough. This might be good enough for my learning class, for my algorithm that wants to learn, or whatever it is you want to do with this data. Let's say you want to be able to reconstruct the data. You want to communicate the data, and the more dimensions you have to write down, the more expensive it is to communicate. So this is the kind of thing that principal component analysis can do, is to figure out what are the most essential dimensions, and then throw away the other ones. So that's the basic idea. In terms of models, there's a similar kind of approach where you can build what's called an autoencoder. An autoencoder takes in images or any kind of structured data, and it has an input, and what it outputs is the same images, which sounds silly, right? Why would you want to do that? It's one thing to take in an image and produce label, but this taking an image and produces literally the same set of images, takes a set of images and produces and outputs the same set of images. Well, the answer is what you do is you force the network to do it based on a fewer number of nodes. So your input here has a certain dimensionality, but by the time you get to the further layers, you have a smaller number of nodes. And the cost, if we're measuring the cost of this particular model, we're going to measure how well the output matches the input. So what we're doing is we train a model, and we're going to talk about some of these. I believe we're going to discuss some of these models in detail, and William's going to discuss them. What we want is for the output to match the input as well as possible, but ultimately, the only way you get here is through here, which means at this point in the entire in the information flow, you've shrunk down this data set into a smaller number of dimensions. That's the only way you can get back to that. So what the model has to do is try to learn some representation that's lower dimensional, that's able to ultimately encode all of this information. Now, if this is white noise, by the way, this is impossible. You'll never be able to do anything. It has to be possible to find some structure that's inherent, it's latent in the inputs, and has to be able to learn what that structure is, and then be able to reconstruct that information. And the same thing is true for principal component analysis. If this was just completely and totally randomly distributed, you'll get nowhere with PCA. If there is no inherent structure for the PCA to take advantage of, all your dimensions are equal, and there's no way you can throw away any of them. Okay, so this gets us to the kind of language that we often use in our lab, which is this idea of basis or dictionary learning. And so the idea behind dictionary learning is to learn some sort of feature set, and we can think of these as dimensions, by which you can reconstruct some set of inputs. So for example, let's say you have a book, and you want to tell somebody else what's in that book. Right? You want to somehow communicate the information in that book. So if you think about a photocopy machine, that's sort of the dumbest possible way of encoding information. What you're doing there in a photocopy, I mean, maybe contemporary photocopy machines have some smarts in them, I'm not sure. But the dumbest way is to literally take every single pixel and write down the value of that pixel. So you've got white, 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 white all over here, and then you have to get some black when you hit the letters, and every single point along the way, you have to write down what the value is, right? This is that, in a way, the least efficient way of encoding a high-dimensional piece of data. What's a more efficient way, potentially, of doing it? So you might notice that there's some patterns in the book, right? It's not random. It's not just black and white pixels. There are things like letters. And not only are there things like letters, there are words. And not only the words, there are words combinations. So what you might want to do is come up with a scheme where what I'm going to communicate to you is not the individual pixel values, but rather what word is there, or maybe even, once upon a time, right? Maybe we've got a specific value that says when I say tell you that, that is what you're going to write down on your end of the communication line. And so this is a way of shrinking the dimensionality. So the big question is, how do you get these kinds of features? How do you learn what the right features are from this kind of input? And so we think the brain does this. There's an idea called sparse coding. So there's 3 flavors of theory as to how the brain encodes information. So taking a little quick pit stop, going back to the brain. So we mentioned yesterday the grandmother cell, and this is the idea that perhaps there's individual neurons whose job it is to encode a specific feature out there in the world, a complex feature, like a specific person's identity, Halle-Berry neuron. Right? This is called a local code. It's also called specificity encoding. It's in some ways very efficient. In some ways, if we think about and we do have to think about this, metabolic resources. The brain is very expensive to run, just like GPUs are expensive, right? Data, just like Bitcoin is expensive. What do we mean? Well, that computation costs money. If we have to use neurons, and we use about 25% of our metabolic energy goes to actually running our brain. That's expensive. Well, this way we're using the fewest neurons to represent information in this kind of local code, but it's a very brittle representation. One big problem with this is if neurons get knocked out, or if neurons are inherently noisy, individual neurons or a very small number of neurons that are encoding for something, it's very brittle and it can break very easily. So the opposite of local coding is dense coding, also called distributed encoding. And so this gives you a very robust representation. If you've kind of distributed your information across many, many neurons, then if one happens to get noisy or knocked out, there's a good chance there's a lot of redundancy there. The problem with this is it's very high metabolic cost. You have all your brain on all the time, which is a seizure, actually. Right? Well, actually happens, right? So our brain's not meant to do that. So there's a compromise position, which is this idea of sparse coding. And sparse coding is that you don't encode in terms of a very small number of neurons, like 1 or 2, but you encode as a distribution across a small number of neurons. And there's significant evidence that in certain parts of our cortex, this is in fact what we're doing. That this is in fact what the neural code looks like. If you look at how often neurons fire, well, they definitely fire more often than just in response to a single kind of object, but they certainly don't respond in response to all objects. So they're not as promiscuous as, say, the retina is, but they're also not quite the Halle-Berry neuron. They don't just seem to respond to one kind of thing. So, a quick idea of sparse coding is it can be ported over, this idea of sparse coding in the brain can be ported over to a computational model. What you can do is ask a computational model to keep things sparse. So this is based on work by Fields and Olshausen, which changed my life. I first encountered sparse coding in a kind of a computational neuroscience retreat where I was first introduced to the work of Fields and Olshausen. And I think it's probably one of the most important findings in computational neuroscience history. And that's the idea that if you give a model this constraint that it has to encode information in a sparse fashion, you end up with something quite remarkable. I'll reserve that for just a moment. So what does it mean? Well, let's say we have natural images, and this is very important. The images have to come from nature. Remember, you have to have that kind of structure that we talked about. Large regions where not much is going on. But every once in a while, things happen. There's objects, there's edges. And so natural images, if you take a natural image and you break it up into patches. So here we're kind of zooming in. Let's pretend this is a patch of this image. And then we're going to take an even smaller portion of this. So imagine we just want to try to encode a set of patches that were 3 by 3. That's just what I'm showing you here. So we've got let's say we're going to train our model on a few natural images. We can take a lot. Unlike a lot of machine learning, you don't necessarily need tons and tons of examples because you can get lots of samples from a single image. You can go across this image and grab a whole bunch of samples of these patches. What we want to do is, so here's a patch, right? Up close, really hard to tell what that might be. But if you take lots and lots of these together, you'll get something that looks like that. What you do is you're asking a model to reconstruct this kind of patch. And we want to do it based on a certain number of features that we're able to activate. So we basically are asking the model to come up with these bases. This is like a basis set. So we could think of these as dimensions. And what we do is take a linear combination of these. We're saying, hey model, give me some features that I can linearly combine to form this. And then we'll take another one. We'll move over and we'll take the next image patch. Okay. Now give me some features that can form that. Now give me some features. Well, how many features? Let's say we gave it 100 or something like that. We'll give it a constraint. There's only a certain number of features you can use. And additionally, not only are there a certain small number of features, but you're only allowed to use a few of them at a time. That's the sparse coding principle. That's the idea that out of 100, you're allowed to choose 6 or something like that. So this is the only equation I'm going to show you, I think, in all of my slides. but it's kind of important, and we don't have to go through it in any great detail. But this is the basic idea of sparse coding, which, as I said, I think is arguably a very fundamental idea in terms of understanding the brain and also understanding how we can arrive at these kinds of efficient codes. And so the basic idea is you want to minimize some cost. You want to find some minimum. And that cost is defined as the reconstruction error. So what that means is, we go back here. Let's say we've trained our model up, a couple of iterations on our model. And then we say, okay, now reconstruct this image by making these patches out of these little features. How well does it match? This is an autoencoder. You take in inputs. You say, okay, given just 100 of these things, and you're only allowed to activate 6 at a time for each patch, how well can you reconstruct the image? And then you measure that. So that's the reconstruction error. So the difference between the original image and then this is just the sum of these particular features multiplied by some coefficient. That tells you how much of it is, so you're just doing a linear combination, how much of each feature you're using. And that's the error term. And it's sum of squares. And then you also have this other piece of this equation that simply measures how many of those features are active. And so that adds to the cost. The more features that are active, the more the cost goes up. So what, of course, this forces the model to do is to try to reduce the number of active features. And what happens if you do that, and so this was Hilshausen and Field finding. Actually, there's an earlier paper. I shouldn't have put that. 1996. What they found is that if you train a model to do this, and there's various different mathematical approaches, you can do it with neural networks, but in fact they didn't. There are other computational approaches to doing this. What you get are features that look like this. Does these look familiar at all? Right, so these are almost pretty much identical to the features that we know are present or being encoded in early layers of visual cortex. So this is probably what V1 is doing. This is, in some ways, you could argue that this is what the math of the brain is. This is the, it's carried out with very different hardware, but in terms of the basic software, in terms of the program that's running in our cortex, this seems to capture quite well what the idea of the system is. Now, this is unsupervised learning. This is simply asking the brain to encode the information in a lower dimensional way that still captures a lot of the essential information. By the way, this is not just true of visual inputs. There's additional evidence that if you use auditory information and sparse code that, the response characteristics, the dictionary that ends up being learned, looks awfully similar to A1, primary auditory cortex. And there's also some evidence for other areas, somatosensory as well. So this seems potentially to be a pretty good estimation of what at least early sensory cortex is doing. Now, I would make the stronger argument that this is probably true all the way up through the cortex. Then when we get face selectivity in inferior temporal cortex, those kinds of face-specific neurons that we've discussed, ultimately it's going to be something having to do with this. During early development, there was a woman who came, Professor Linda Smith, I think is her name, who visited us a few years back, and she puts a GoPro on babies' heads and just wants to see what do babies see. And it turns out that some astoundingly high percentage of their early visual experience, I want to say somewhere in the range of 75%, but that sounds too high. But it was a few years back. Consists of one particular kind of stimulus. Anybody, what is that stimulus? Anyone want to guess? Faces. They see them all the time. Babies, whenever a baby's awake, especially in the early months of their life, there's somebody in that image who's either there or right in there. It doesn't mean that it's taking up the whole image, but there's a face around there. So the faces are things that the early baby brain has to try to encode, it efficiently. And it seems perhaps that that's where this fusiform face area has its origins. So this is all happening, again, it's kind of unsupervised, not because it's a labeled piece of data that's going to be useful for any specific task per se, but rather the brain is simply trying to say, how do I take this absurdly high flow of information, 100 million measurements in each eye, about 50 times a second. How do I store this information in a useful way? Well, perhaps this is an insight into how that's done. Yes?
In the equation that you showed, the final term that you said was added to the cost?
Yes.
You said add number of active areas?
The number of active features.
Features.
So
what does that mean exactly?
So it means these guys here. So let's say we have about 100 of these that we're able to learn. And we want to create, so for any given new input, we want to reconstruct it using some linear combination of some set of these features. Question is, how many are we allowed to use to reconstruct any given input? Right? Optimally, if you really want to be optimal, if you let the model use all of them, it can do presumably that'd be the best.
Then you have high cost. I see.
But then you have high cost in terms of activation.
Regarding the face, the babies looking faces. This is not something you can deal with in this talk, but it's interesting because if a baby is born with a genetic, or if you're born with genetic prosopagnosia, and all of the sort of input cortical visual areas are doing their coding,
doing their job.
What in the heck is it that's exactly missing in the face area?
Good question. Very good question. And there's still a tremendous amount of controversy about how the face selective area gets its characteristics, what it means. Some people propose that it's there from birth, that there's some predisposition towards face-like stimuli. I think Occam's razor, would dictate that probably not. That it probably can be encoded based on specific on experience. But that's a very good question, and one that would depend, right? The answer to that question would be very informative about what goes wrong in the case of prosopagnosia. So for those who are not familiar, prosopagnosia is face blindness. People who can otherwise pretty much are just able to see and recognize pretty much all classes of objects except faces. And it turns out that faces are a special kind of class. The question is why. And so just very briefly, the controversy surrounds whether it's because faces are this kind of ecologically important category, and that there's a specific type of brain area that is primed to learn faces, and there's something wrong during perhaps genetically or happens developmentally. Alternatively, another explanation is that discriminating faces requires a very high degree of sensitivity to differences within a specific class, because all faces are quite similar, especially within a specific ethnicity that you might be an expert in. You're able to discriminate think about your siblings that look kind of similar. Well, a member of the family is able to discriminate between those siblings, or most people can discriminate between those siblings. Now, of course, but those two faces, of course, are very similar visually relative to some other class of stimuli, right? A face versus, a computer. So that's the other alternative sort of explanation of what that face area is doing, is that it develops this kind of expertise in highly similar classes of stimuli. So I think a lot of this rides on whether you kind of believe this computational story. My money's on the idea that it's really based on developmental experience, and that it's an efficient way of encoding what ends up being a very common stimulus that we encounter a lot.
And besides, related to what he's saying, if you observe, we are dealing on still images. So the objects of the image they don't have motion. What happens if the objects of the image are in motion? They have moved. And do the values of the feature change or they don't change?
That's a good question.
How do you reconstruct the original image?
Yeah, and that's going to be an important avenue of research going forward in machine learning. The vast majority of machine learning is supervised learning. The vast majority of machine learning is individual images, static images that are presented to the classifier. But in the real world, of course, things are moving around. Well, the answer is we know in the brain that there are neurons that specifically encode for motion. And so that is another type of feature, right? A leftward motion, a rightward motion, up, down, rotational. These are all things that are probably encoded in neurons as a feature. So the certain kinds of motion are probably encoded as features. And then you combine those features with the static, and basically you're able to get moving objects, something along those lines. I would refer you to my colleague Howard Hawk, who's far more expert than I am in modeling motion detection. But it's an active area of research, but not quite there yet, because there's so much to be gained from mining just static images, right? You can do a lot, right? We can do radiology without really worrying about motion, as long as your images are captured in a static way. So there's too much opportunity right now for people to be worrying that much about that. But it's something actually in our lab that we're exploring pretty heavily. So, for example, in navigation, right, in when you're driving, you might want to really encode a sequence rather than just encoding individual static frames. So, we actually have some evidence that it actually helps you drive. Ask Reggie about it if you go on to the breakout dinner. Okay, so just to sort of cap it off, it's very clear that in some sense we perceive with these predetermined kinds of features. So these are called the Losery Contours. And so what's the magic here? There's no triangle here. There's no white triangle here. It's not really there. And there's no ball here. And there's no curved triangular type of shape here as well. So why do we see a triangle? Right? It's very hard. Not only do you see the triangle, it looks a little bit lighter in color. Right? Doesn't this look a little bit lighter than that? Mm-hmm. Your brain's making that up. Right? It's not lighter at all. It's just the same exact thing as here and here. And there's no triangle here at all. Well, one way to think about this is if you have these predetermined features, what your brain is doing is not trying to encode the actual input, the retinal input. What it's doing is looking for evidence that some feature that you've learned is often in the world is present. And so triangles are frequent, or certainly oriented edges are common. And therefore, if you've got some evidence here and here and here and here and here, right, this little point here, that's enough. It's just enough evidence right there from a small kind of sample of evidence that might be sufficient to activate that feature that says that there's a line there. And once you do that, you can't go back. Your brain is like, that's a line. Doesn't matter what you know. Doesn't matter how many times you stare at this thing. I've seen it hundreds of times. You still can't help but see the edges there. And the same thing goes for the circle, right? Circles are very common. We see them a lot. Curved edges. That's a kind of structure we see very frequently. Well, there's sufficient evidence just from a couple of these convergent points here that you end up seeing it. Here's a nice illusion that demonstrates this idea in relation to this higher level feature, faces. Pull this up.
Thomas, Papa Thomas.
Guess what nationality he is. So he didn't actually discover this, but he did a great job of kind of demonstrating it. I saw this live when I visited Rutgers. So did anybody catch what just happened there? Okay, watch it again.
Boing.
Right, so is the nose sticking in or out?
Out, of course. That's cool.
And, right, this nose ring looks like it's moving, but that's not actually what's happening. It looks like it's sort of orienting towards us, but there, right at that moment, you can see the trick. So our brain overrides, very quickly overrides what is the only reasonable explanation of this, which is that it's a hollow mask rotating. And that's in fact what it is. But very quickly our brain says, no, that's not what it is at all. It's actually a face. It just turned from a mask into a face. And you're like, brain, hello? What are you thinking? But it doesn't matter. Why? Well, because we have a great deal of experience with convex faces, right? Noses that stick out. And so this is a feature that's waiting to be activated. And we have very little experience with concave noses that are sticking in, which in fact this is what it is. And it's ambiguous, it's inherently ambiguous in the image, right? There's depth shading information here that's completely ambiguous as to whether it's, I should have showed your illusion. Ask Russ to show you a really cool version of this kind of depth reversal, if you get a chance. And so the point is that you have these features, these dictionary elements that are kind of primed and ready to go. And if there's sufficient evidence for them, your brain is going to say, that's a nose. And you're going to see it extending out of the image versus in the image. And one last demo here that I particularly like is where you can actually see these dictionaries being formed in real time. So there's a phenomenon called sine wave speech. And so all sound, of course, consists of just different frequencies of pressure, of oscillatory pressure in the air reaching our inner ear, and then there are these hair cells that are sensitive to these different frequencies. When I'm talking, a natural voice contains a very large, broad range of different frequencies. What sine wave speech consists of is taking that big, broad range and throwing away a bunch of those frequencies. Another way of thinking that is dimensionality reduction. You're throwing away a bunch of the dimensions of that data. And what you will find if you listen to it, let's pull up this, is that it sounds really weird and doesn't sound like much. Let's listen to this one. Okay, so this probably does not sound like speech. Maybe it sounds a little like R2-D2. Right? Okay, so here's where the crazy thing happens. What I'm going to do is prime you to. Now here's where the magic happens. Let's listen to that one again, the original one.
Oh my God!
Totally different, right? Let's try another. Believe it or not, I recognize. I've heard this enough times that I hear it.
No. Oh my God!
Right, very clear. So what we've done here is we've provided now some expectation about other dimensions that aren't really in there, but that we've now, to some extent, correlated with the existing dimensions in the data. So in some ways, we've created new features that are ready to be selected. And so when you hear the original low-dimensional stimulus, your brain fills in those additional dimensions. It's not really there. Let's do one last one. Sometimes
it's not really
people
there,
can
but
learn
you're not going to hear some random sentence. You're
What do
always
you
going to
mean?
hear the same sentence.
Oh, well, you hear just right, but you're primed now
Once
for
you've been
those
primed.
specific, right, but just for those specific features that are consistent with this particular set.
Yeah.
Do they have ones where there's two different real sentences that match up to that not real one that you can make it switch back and forth?
Two different real sentences.
Like how
Oh,
you
that's interesting. You mean, in other words, well, that's interesting. In other words, they have the same sine wave speech representation,
correct.
but
Where I can,
I've never seen that. That's a cool idea, though. I don't know how easy that would be to do. Because bear in mind, even though it's pretty low dimensional, but it's sufficient to be really specific, actually. There's not very often going to be, so this is like sparse coding. Even with just a few number of dimensions, that's very likely to pick out something quite specific, right? Because that's, combination of 5 amongst 100 is still very rare that you have that exact combination. So even the sine wave, the idea that it would be consistent with two different sentences, it'd be interesting, but it would take a lot of time to work that out. If somebody can do that, that would be really cool.
Kind of the inverse example is, brainstorm green needle.
Yeah.
Did you see that one?
Yes.
It's all completely semantically.
Have people seen that, the
cognitively-
brainstorm green needle demo? Do we have time? Real quick. It's so cool.
It may not work. It depends on which microphone is being used, whether it works or not. Because I tried it on my computer and it's.
Yeah, that's actually the closest thing to what you're talking about, where there's actually two completely and different high-level sort of filling in the dimensions that are consistent with.
It's
This
in your
is it.
You have to think in your mind either the word.
Actually, there's a better one where you can get it to flip. Which one was that?
The 10 different ones. I'm gonna try to find it.
Well, this one you can get it flipped.
All right, here we go.
Think brainstorm or green needle, whichever one you think you will hear. Now.
How many purple are brainstorm?
brainstorm.
Okay.
Okay, now think hard. Green needle.
Green needle.
Yeah. Works pretty well, right? And with that, his brain broke. That was it.
Sorry.
We'll get you. Sorry. Okay, so that's all I've got.
Sorry.
But here's sort of the big picture story is that we don't see what's actually on our retina. We don't see even what's in our probably early visual cortex, and we don't hear what's on our ears. What we do is we construct some internal representation that is heavily dependent on our own interpretation, right? So it's really a great deal, in some way. I don't know how you can measure. I've never seen a convincing or compelling measurement of how much of our perceptual experience is based on what we call bottom-up information, or the actual sensory information, versus the top-down. But we've got these features ready to go. We see faces here because we've seen faces so many times before. We just have sufficient evidence that there's a face here, and we end up perceiving that as a face, but not because we're actually doing all the hard work of perceiving every detail of this stimulus. So in some ways, we're living in the matrix. It's a matrix made up of all of our past experience forming this much lower dimensional representation of the environment. And then what our brain is trying to do is say, which of these lower dimensional dimensions, which of these dimensions, or really what point in that lower dimensional space are we in right now, based on this higher dimensional input? And with that,
I found the one. Let me see if I can
okay.
pull this up. Let's see if I can find this real quick.
While he's doing that, the illusory contours that you showed, in some sense, I don't think it's exactly analogous to a dictionary learning, or because it represents an active process in the cortex, I believe, of long-range interaction that is dynamic.
But still, by the time you get to V2,
right,
what you've got are neurons that you cannot distinguish based on their activation.
they will respond
It's
to.
equivalent to
Yeah.
whether it was driven by. So
Yeah,
the
that's
long-range
true.
interactions may be required in order to drive that, but by the time you're at a little bit higher up in the matrix,
That's true, yes.
it's as if that edge was there. So those features are kind of looking for the evidence that they should be activated.
This one's crazy. This one has like 10 different percepts. See if you can figure out what this is saying. I know it's kind of loud and weird and strange. All right, so I know, sorry, it's like kind of crazy, but
This is Jenny and Laura.
yeah. So now listen for the words dog's version. Now listen for dad's prancing. Hang on. Listen for Tom's crazy. Listen for dad's braces. Hey, listen for divergent.
Divergent I heard.
Listen for outrageous. All right, we'll leave it at that.
Suffice it to say that the natural world is pretty ambiguous.
What is he actually saying?
I'm curious, on the one with the brainstorm and the green needle, can you go back and forth? Or is it just going to go one way?
Does everybody know?
Because that's what I'm curious of, is the switcher sounds exactly. I want to hear brainstorm again.
So maybe if we just turn the volume down just like a little bit.
We'll do that.
All right.
Try to hear brain needle.
Brain needle.
Brain needle.
Yeah.
You heard brain needle.
Yeah.
Now listen for green storm.
Yeah. Yeah.
Okay, so like all four are stable.
But you can't just generate any one. By the way, that little kid was saying sparse coding.
Right, yeah. Exactly.